ഇതാണ് ചോദ്യം. A neutral pion നമ്മൾ ചെയ്തിട്ടില്ലാന്ന് തോന്നുന്നു അല്ലേ? A neutral pion of mass m and momentum അത് ചെയ്താണോ?
ഇല്ല.
A neutral pion എഴുതണ്ടല്ലോ അല്ലേ? A neutral pion of mass m. Okay, ഇപ്പൊ pion ഉണ്ട്, it's mass m and momentum mass തന്നിട്ടുണ്ട്. Mass is equal to, we are talking about a pion, a neutral pion, mass m, momentum is given, okay, 3/4 mc. 3/4 mc decays into 2 photons. One of the photons is emitted in the same direction as the original pion and the other in the opposite direction. Okay. So in the opposite direction, find the energy of each photon, right? Find the energy of each photon. So the interaction that we are talking about is this. Pi gives neutral pion decays into 2 photons. We'll call it as A and B. All right. Now they are going in opposite directions. Okay, so we have only one dimension. They are going in opposite direction. One of the photons is going in the same direction as the incident pion. Okay, as the pion with momentum 3/4 mc. So there's a pion coming here. There's a pion coming here, and one of the photons goes in this direction, and the other one goes to this direction. All right. So we have only 2 directions here because it's one dimension. That's the thing that we'll be using here. Okay. Now, I think it's easy to do this in the usual energy momentum conservation thing. Okay. So let's see what we have. Let's see what here. The momentum is given. Momentum of the initial pion is given. So if the momentum is given, we know how to find the energy. Okay. So I'll write it like this: P pi vector. Okay. Modulus P pi vector is equal to 3/4 mc. Okay. So once the momentum is given, we know how to find the energy. This formula I said is very useful. We can use it. We can do it like this. It is, you know that E square is equal to P square. Yeah. E square is equal to P square C square plus m square c raised to 4. So that's equal to, just substitute this, 9/16 P square. E square is equal to P square C square plus m square c raised to 4, right? So that is, when you square this, it becomes 9/16 m square c square. There's a c square here. So m square c raised to 4 plus m square c raised to 4. So that's equal to 25/16 m square c square. In other words, the energy of the pion is 5/4 mc. Okay, now we have got the energy and we have got the momentum. All right. So now let's write down the equation for energy conservation. Energy conservation. Energy conservation. So equation of energy conservation says that E pi has to be equal to EA plus EB. All right. Okay. Now, so from here we see that 5/4. Sorry, here is mc square. Okay, mc square. It's 0 raised to 4. 5/4 mc square is equal to EA plus EB. Okay, that's the conservation of energy. Okay. Now let's look at momentum conservation. Okay, by momentum conservation we mean for 3 momentum conservation. Okay, 3 momentum conservation. You can also do this using 4 vectors, but this is easier here. Okay. In this case, this method is easier. So momentum conservation says that PA vector plus PB vector is equal to P pi vector. Okay. Now we said there's only one direction. There's only one dimension. Okay. PA, let's say that PA and PB, PA and P pi are in the same direction. Right. And particle B, so yeah, B is moving in the opposite direction. Let's imagine like this. Okay. There's a pion that comes here, and then you have got A moving this way and B moving this way. Okay. So the momentum 3 vector of the pion and particle A is of the same direction. Okay. So we can write it like this. We can simply write this as, okay, So the direction we can, because there's only one dimension, we can get the direction by minus and plus. Okay, the incident direction will take us plus, the opposite direction will take it as minus. All right. So this means that here, this means that modulus of PA vector, the direction is plus here. Okay, minus modulus of PB vector. Okay, this is the magnitude of PB vector, and this is the direction. Is that clear? Okay, is equal to modulus of P pi.
Yes, sir.
So from here you see that now this for photon, right? For photon, what's the momentum for photon? What we need to find is the energy. What we need to find is the energy. Okay? So what's the expression for momentum of a photon? We know that E square is equal to P square C square plus M square C raised to 4. For a photon, the mass is 0. So E is equal to PC, okay? Or P is equal to E divided by C. Okay? So we can use that here. EA by C minus EB by C is equal to what's P pi? That's equal to 3 by 4 MC, or EA minus EB is equal to, we can multiply throughout by C. So EA minus EB is equal to 3 by 4 MC square. All right. So we have got two equations. We have got EA plus EB equal to 5 by 4 MC square. I think I'll just write it here. We have got EA plus EB is equal to 5 by 4 MC square. And we have got EA minus EB is equal to, what was it? 3 by 4 MC square. Okay, now we have got two unknowns and two equations. We just solve this. Okay, for example, you can add these two, and you see that 2EA is equal to 8. So this is 5 plus 3 is 8. 8 by 4, 2 MC square. Or EA is simply is equal to MC square. Okay, that's the energy of one photon. Okay, what's the energy of the other photon? We just use the energy conservation because we know that EB is equal to 5 by 4 MC square minus EA. So that's equal to 5 by 4 MC square minus MC square. So that's equal to 1 by 4 MC square. That is EB. Okay, so that's how you find that. So remember that when you have massless particle, you can write energy as PC or P as E by C. All right. Now this immediately will eliminate this relation will immediately eliminate one of the unknowns. Right. If you know the energy, you can write it in terms of momentum. If you know the momentum, you can write it in terms of energy. All right. Basically, we are using this relation here. This relation is very useful because if you know the momentum, okay, you can get the energy, or if you know the energy, you can get the momentum. All right. P, so this is not E square, E. P square is equal to E square by C square minus, this is M square C raised to 4, I'm sorry, right? E is equal to square root of P square C square plus M square C raised to 4, or you can also find P in terms of energy from this relation, right? This is very useful. You will be able to get quick answers using this, okay? Another problem. This question, okay, they may ask which of the following is true, right? For example, E minus plus E plus gives a photon, all right? So this reaction means an electron and a positron annihilate to give a photon, okay? Is this process possible? Is this process possible? Is this process possible? Okay, is this possible?
രണ്ട് ഫോട്ടോൺ
രണ്ട് ഫോട്ടോൺ പോസിബിൾ ആണ്, ഇത് പോസിബിൾ അല്ല. അതുപോലെ ഈ ഡീക്കേയും പോസിബിൾ അല്ല. This also is not.
രണ്ട് ഗാമാ റേ പ്രൊഡ്യൂസ് ചെയ്യുന്ന ഓപ്പോസിറ്റ് ഡയറക്ഷൻ.
Yes, that's correct. Okay, otherwise the energy and momentum conservation will not be valid. Okay, so for the record, I'll just give the argument here. This interaction, this reaction is not possible. Okay, it can be easily seen if you go to a center of mass frame. In center of mass frame, if you go to center of mass frame of these two particles, all right, the positron, then the momentum, total momentum is equal to 0. All right, this means that the total momentum of on the right hand side also has to be 0 by energy conservation. by energy conservation, okay, P gamma has to be equal to 0. All right, P gamma has to be equal to 0. Now this is not possible because a photon always travels at C. Not possible because photon always travels at the same speed. Okay, it cannot, there's no rest frame for a photon. So that's the reason why this interaction is not possible. You'll need 2 photons, then that is allowed. But if there are 2 photons, it is allowed. Okay. Okay, let's look at another problem. A particle of mass m and energy E decays into 2 identical particles. In the lab frame, one of them is emitted at a 90-degree angle, right? So I'll just write a particle of mass m and energy E decays into 2 identical particles. In the lab frame, one of them is emitted at a 90-degree angle. One of them is emitted at a 90-degree angle. Okay, so we have got something like this. We have got a particle of mass m coming like that, and there's a particle which is emitted at 90-degree angle with the direction of incidence. Okay, what are the energies of the created particles? What are the energies of the created particle? Okay. Now this is one question where the convenience of using form momentum becomes very clear, right? So we've got a situation like this. Now this is a difficult situation. We have got 2 particles here. Let's say this momentum is P, this is P1, and this is P2. All right. So we have got, this is form momentum. All right. We have got P going to P1 and P2. All right. Now you will have to take this angle theta. All right. You will have to take this angle theta, and then you will have to write the momentum conservation, the energy conservation and form momentum conservation separately, which will involve cos theta, sin theta, tan theta, etc. Okay, you can try that. All right, you can try that. Try using energy conservation and momentum conservation. Right, so it will involve some angles, including tan theta, etc. Okay, that is not very easy to do. For example, if you let's just see 1 second. Okay, you can try that. Okay, can't find it here. Oh, yes. Right. So all right, so we can, for example, if you write the energy of or the form momentum, the components like this, initial particle, we can take it as energy E1. Okay, we imagine it's moving along the x direction or y direction or z direction. Okay, let's say it's moving along the x-axis. Right, so we can write it as, we'll write P is equal to E comma P comma 0 comma 0. Right, the 4 components. All right, and you can write P1, the outgoing particle, one of the outgoing particles, as we'll write it as E, okay, 0, okay, because this angle is 90, all right? So the component along the x direction, the x component is 0. It's P1. This is simply P1 sine 90, all right? All right, 0, and the y component is P1 and the z component is 0. Okay, there's only y component here. Am I right? Okay. Similarly, you can write P2. P2 is even more complicated. This is theta, so you have got E2, okay, and P2 cos theta, P2 cos theta, and you have got minus P2 sin theta and 0, right? Minus P2 sin theta and 0, okay. All right. So now if you look at this, these are the three moments. There is this cos theta, you have got the sin theta. Okay, if you find the energy, it will introduce tan square theta, etc., tan theta, etc. This will be complicated, right? So the simple way to forget about all these things, there's a simple way to do this using 4 vectors. That's what we will actually do. You try this method, okay? You have to try this one. Try this, okay? All right. So I'll do it in the for moment using for moment, and you will see that we can do it without introducing any theta at all. Right? That shows the convenience of this. So we can write the for momentum conservation P is equal to P1 plus P2. We can write P is equal to P1 plus P2. Okay, and then you can write this is just for momentum conservation. Okay, now what we do is that you see that this expression for P2 is complicated, right? The expression for P2 is complicated. There's cos theta, sin theta, etc. So what we do is that we isolate this P2. Okay, P minus P1 is equal to P2. Right? This is for momentum. Now you square on both sides. Okay. Square means it's a 4 vector square. Right? So you see that P square plus P1 square minus 2P dot P1 is equal to P2 square, right? But what's P2 square? So P square is, let's say, M square C square, and P1 square is M1 square C square, okay, minus 2 P dot P1. So we have to write the components. Let's write it as E by C, comma. We only had it along the x direction, right? 0, 0. Okay, and this we'll write it as P1. What were the components of P1? Okay, you have got E0, P0, right? There's only the y component. Am I right? There's only the y component. So this I'll write it as E1 by C. Okay, 0, P0. Is this clear? Now this is equal to M2 square C square. Okay, M2 square C square, right? And so they said that the particles are identical, right? The particles are identical, which means that M1 and M2 are the same, right? M1 and M2 are the same. Now you see that what we have done here is that we have this for momentum P2, but we isolated it, right? And when you squared, what happened is that you just get M2 square, sorry, M square C square. Right? When you square it, you get M square C square. You see that we have already eliminated all that sin theta, cos theta, all these problematic terms are gone. All right, we don't have to deal with them. Now, this is convenient. Now you see that M square C square plus M square C square minus, this would be 2E E1 by C square. Okay, 2E E1 by C square. We have multiplied the 0th component. Okay, and then minus the spatial part, minus the scalar product of the spatial part. All right, but you see that P with 0. Okay, the x component is 0. The product of y components is also 0. The product of z components is also equal to 0. So this is equal to M square C square. You see that we have eliminated all the problematic terms. Okay, now you just solve for E1, and that's your answer. How do you solve for E1? You see that 2E E1 by C square, isolate this term, that's equal to, so these terms gets cancelled, right? M square C square gone. So this is equal to M square C square, and E1 is equal to M square C raised to 4 divided by 2E. Okay, we got the energy, right? Now, if you continue along, if you do momentum and energy separation, you will see that there are complicated terms coming up here. Okay? We can, of course, write this momentum in terms of the energy because that's what we have to find. But then you will find all this cos square theta, 1 minus cos square theta, 1 plus cos square theta, and all these terms. It's a bit more complicated, right? Now, here we eliminated all those problems just by isolating this P2 and then squaring it. Okay, so everything is gone, everything is hidden inside this simple term. Okay, now we have got E1. How to find E2? We know that E1 plus E2 is equal to E. All right, so E2 is simply E minus E1. All right, so that's equal to, I'll write it here. So E2 is equal to E minus m square c raised to 4 divided by 2e. Okay, so you can write it as that's equal to 2e square minus m square c raised to 4 divided by 2e. Okay, this is E2. So we have got E1 and we have got E2. This is the this is the answer that we have to find out. Okay, so that's a, you will see, you can try you must try the other method. Okay, it's not very difficult, but you see that it takes more time. It takes more time. This is much quicker. All right. Okay, now there is a small topic called relativistic dynamics. I'll try to find more problems from this particle collision, the collision problems. I have actually discussed all the problems that I could find in the, so most of these questions that I discussed are asked in the previous net JRF questions. Okay, the others I found from other textbooks. All right. So relativistic dynamics, there used to be a question from, there was once a question from this part. Okay, relativistic dynamics. Okay. Relativistic dynamics, what do you mean? You need the equation of motion, all right? You need the equation of motion. For non-relativistic, we know that the equation of motion is F is equal to, I'll write the vector equation, F vector is equal to dp by dt. This is the equation of evolution, all right? This is known as, what they say, Newton's second law. Right? The thing for relativity is that it obeys the same evolution equation. All right, it obeys Newton's second law exactly in this form, only if you substitute p vector by the corresponding relativistic momentum. All right, so for relativistically also relativistic. Okay, this is non-relativistic, and here p is equal to mv. All right, in relativistic, this is equal to d by dp by dt. Only thing is that you should have p is equal to gamma mv vector. All right. So if you change the momentum to the corresponding relativistic momentum, you get the relativistic dynamics. Okay, this is simple. All right. Now this is the convenience of using the same mass. Okay, this is convenience of using, not worrying about the new concepts like relativistic mass, etc. This gives you a direct generalization. Okay, so F equal to dp by dt is the equation of evolution. Okay. Now there was a problem from this part. Once there was a problem. Okay, so the problem is regarding motion under a constant force. Motion under a constant force. Motion under a constant force. Okay. So the question goes like this: a particle of mass m is subject to a constant force F. A particle of mass m is subjected to a constant force. Okay, a constant force. A constant force. Let's call it as F. All right, constant force F. Okay. If it starts from rest, so the initial condition is given. If it starts from rest, at the origin, if it starts from rest at the origin, at time t is equal to 0. If it starts from the origin at time t equal to 0, find its position x. Find its position x, okay, as a function of time. 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 Now, how do we do this? Okay. Now, the question that was asked in the previous net question was to find the velocity as a function of time, right? So, if you integrate the equation of motion once, you get the velocity. You can solve for the velocity. You have to integrate it twice to get the position, all right? So, in the net exam, they asked you to find the velocity as a function of time. All right. So here we'll do one more step and find the position as a function of time. All right. The next exam, they can ask the position also. So we write the equation of motion. The first thing we do is that we write the equation of motion. Right. Solution goes like this. We'll write the equation of motion. F is equal to dp by dt. F is equal to dp by dt. Now you integrate this because f is a constant. You know that. This means that dp is equal to integral f dt plus a constant. There has to be a constant. All right. So that's equal to simply ft, because f is a constant. Ft plus a constant. That's the expression for. So this is p. P is equal to integral f dt. So it's ft plus a constant. Now this is fine. We need to fix the constant. Okay, for that we use the initial condition. It starts from rest, which means that at t equal to 0, p is equal to 0. Okay, this is the three momentum. All right, p is equal to, so I'll write it like this. That's given. All right, so you put t equal to 0 and put p equal to 0. You see that the constant is equal to 0. All right, so you get the relation p is equal to ft. Fine, this is good. All right, p is equal to ft. Now this would be exactly the same if you do for a constant force in the case of Newton case also. Right? Newtonian mechanics also, p will be equal to ft for a constant force. All right, but when you find the velocity, this means that gamma mu, you need to find the velocity first. So gamma mu is equal to ft. This means that mu divided by square root of 1 minus u square by c square is equal to ft. All right. Now you can square this and see, okay, you can say you square this and cross multiply. So you see that m square u square is equal to f square t square multiplied by 1 minus u square by c square. Okay. Now you can just bring this u square, isolate this u square term. So you pull this u square outside. You see that it's equal to u square multiplied by m square plus, okay, because there's a minus here, bring it this side, f square t square divided by c square, so u square by c square. So I will just rearrange this. Okay, this is equal to f square t square, and then correspondingly u is equal to ft divided by square root of m square plus f square t square divided by c square. Correct? Now, in the answer, it was given in a slightly different form. You pull this m square outside of this. So, ft divided by m. We pull this m square outside of it. So, it's 1 plus f square t square divided by m square c square. Or we can take this m to the top, and then you see that u is equal to ft divided by m, right, divided by square root of 1 plus ft by m square c square, ft by m square, sorry, ft by mc square. Okay, so that you get the same term here and here, right? So this is the velocity. This is u of t, u as a function of t, right? Now this is the question that was asked for, I think it was in June 2012 or something. Okay, u of t is equal to ft by m divided by square root of 1 plus ft by m mc whole square, right? Okay. Yes, that's correct. All right. Now you need to find the position as a function of time. All right. Position as a function of time. position as a function of time. All right. So we know that. Sorry. Just give me a moment. Yes. Okay, so we have got velocity as a function of time. All right. Now we know that u is equal to u of t is equal to dx by dt. Right. So we have got dx by dt is equal to f by m multiplied by t divided by square root of 1 plus ft by mc square. Right? Now you have to integrate to find t. X of t is equal to integral f by m t divided by square root of 1 plus ft by mc square dt. Right? Now there are different ways to integrate this. Okay, so you can integrate this and then find it as an indefinite integral and then add a constant and find this constant. Well, that's one way to do that. Okay. Otherwise, we know that the initial position is given. It starts at the origin, starts at rest at the origin. Right? We can also do it as a definite integral. Right? Because we can use the initial condition as the limit here. Okay, you can do it both ways. So you just integrate from 0 to t because we need x of t. Right? So when you write 0 to t, it's not nice to have this same t here because this is just an integration variable. So we put it at dt prime. Is that clear? Now you have to integrate this. Right? Now you have to integrate this. How do you integrate this? I think this is a very easy integration. Okay. So maybe it's easiest if you make the substitution. Right? You can make the substitution. You put
sign inverse അങ്ങനെ വല്ലതും പറ്റുമോ സാറേ?
അല്ല, അത്ര ബുദ്ധിമുട്ടില്ല, അതിനേക്കാളും എളുപ്പത്തിൽ കിട്ടും. ഓക്കെ, അത് എളുപ്പം കാണണമെങ്കിൽ ഇങ്ങനെ എഴുതാം മതി. ക്യാൻ റൈറ്റ് ഇറ്റ് ആസ് മേബി ഓക്കെ, ഇറ്റ്സ് ഈസിയർ ടു സീ ഇഫ് യു പുട്ട് ft prime by mc, you put it as y. Okay. All right, ft prime by mc, put it as y. So wherever t prime comes, you will put it as mc by f multiplied by y. Okay, and wherever dt prime comes, you will write it as mc by f multiplied by dy. Okay. Now you make the substitution. Also, you have to take care of the limits. All right, you have to take care of the limits when you make the substitution. So when t prime equal to 0 means y is equal to 0. When t prime equal to t, okay, what's the corresponding y? T prime equal to t, y is equal to, okay, y is equal to ft by mc. Right? Is that correct? Yes.
Yes.
Okay, so we can write this integration as x of t is equal to integral, okay, 0 to ft by mc. All right, 0 to ft by mc. Or maybe we'll simply write as y, 0 to y. That's also fine. We can write as 0 to y. And then because y is ft by mc in there. No, but better write it as ft by mc. All right, we don't want to confuse. Okay. Now this integral becomes f by m t prime. So what's t prime? So this is f by m. Right? T prime is equal to mc by f multiplied by y. Right? And you also have a dt prime there. Dt prime is mc by f multiplied by dy. Right? Just making substitution. And in the denominator, you have got 1 plus y square. Am I right? So integration is over. Is this correct? Yes.
Yes. C by FT by
ശരിയല്ലേ? ഇനി ഇവിടെ ചെയ്യാം, അല്ലെങ്കിൽ പിന്നെ അടുത്ത്.
dt.
ഇന്റഗ്രേഷൻ വളരെ എളുപ്പമാണ്. നമ്മൾ ജസ്റ്റ് ഒന്ന് സബ്സ്റ്റിറ്റ്യൂട്ട് ചെയ്ത് കഴിഞ്ഞാൽ സിമ്പിൾ ഫോമിലേക്ക് വരുന്നതാണ്. ഓക്കെ. All right, I'll do it here. Okay, so that's equal to x of t is equal to so this f by m. All right, you have got mc by f, mc by f, so that you can pull out. Okay, so I'll write it like this. F by m is a constant. Okay, you also have mc by f square as a constant. All right, and then you simply have y dy divided by square root of 1 plus y square. Okay, ഈ y ഇവിടെ ഇല്ലെങ്കിൽ പറഞ്ഞ ശരിയാ, സൈൻ ഇൻവേഴ്സ് അങ്ങനെ എന്തെങ്കിലും കിട്ടാൻ സൈൻ ഇൻവേഴ്സ് അപ്പോൾ അല്ലേ, അങ്ങനെ ഒന്നാ വരും. y ഇവിടെ ഇല്ലെങ്കിൽ കോസ് ഇൻവേഴ്സോ സൈൻ ഇൻവേഴ്സോ എന്താണ്, പക്ഷെ ഇവിടെ y ഉള്ളതുകൊണ്ട് നമുക്കിത് അറിയാം. Okay, for example, if you just look at this, all right, you know that this is the inverse. We know that integration is inverse of differential. All right, we know that if you take the derivative d by dy of so this is 0 to that particular limit. Okay, d by dy of square root of 1 plus y square would be 1 divided by 2 square root of 1 plus y square multiplied by 2y, right? So y divided by square root of 1 plus y square dy. Okay, or simply if you take d of square root of 1 plus y square would be this. Okay, so this is simply the derivative of square root of 1 plus y square. Okay, so you see that x of t is equal to, we'll write it here, f by m, mc by f whole square. Okay, so this is simply the derivative of square root of 1 plus y square. Am I right? Yes. So that means that you can cancel the integration and the derivative, and you will have 1 plus y square. Not only that, you have to apply the limit. There is a 0 here, and here you have got ft by mc. Okay. All right. So that becomes this m. We can now cancel these terms, I think, right? Yeah. So this becomes you have got f. So yeah, this can be written as mc square divided by s. Okay, just cancel off the terms, multiplied by 1 plus, okay, 1 plus, this is ft by mc square. Okay, 1 plus ft by mc square, and then you also have to apply the limit for 0, right? I'm sorry, there's a square root here. There's a square root. Okay, square root. And if you substitute the lower limit 0, this term I have pulled outside, so this is simply 1. All right, if you put the lower limit, you put y equal to 0, this becomes minus 1. Okay, that's our answer. Okay. All right, that's our answer. That's the correct answer. Okay. Now this is this is how the position versus time, the position of a relativistic particle, which is under the influence of a constant force, it will go like this. All right, so I'll just write it here. We have got x of t, okay, of a particle under constant forces, mc square divided by f multiplied by square root of 1 plus ft by mc square minus 1. All right, so this is it. All right, that's the answer. That's the correct answer. This can be asked for the exam, right? Because in one question the velocity was asked. Now they can ask the position. All right. Now, for example, an example of this such a system is a charged particle. For example, a charged particle, okay, in a uniform electric field. Uniform electric field. Okay, so this equation gives you the trajectory the trajectory of a charged particle, for example, in a uniform electric field. Uniform means an electric field that does not change with time and space. It does not depend on position or time. That means you have a constant force. Correspondingly, you have a constant force. So a charged particle, okay, the charged particle in an electric field would follow this trajectory. Now, if you look at the space-time diagram, you'll see that there is something instructive. If you look at the space-time diagram, usually in Newtonian case, we used to write x here and ct here, but this is the new convention that we use. If you're looking at non-relativistic particle, okay, if you're looking at non-relativistic particle, it would be a hyperbola like that. All right. So x of t is equal to, if you take non-relativistic, f by 2m t square. Newtonian case, if you for constant force, you said it's a hyperbola, which means that the slope, there's no limit on this slope. Okay, the slope can increase, which means that the velocity can keep on increasing and it can go up to infinity. Okay, this is Newtonian. Okay, the slope can keep on increasing, which means that the velocity, because you are applying a constant force, it keeps on getting accelerated, right? F equal to ma. Okay, can go up to infinity. Okay, but we know that this is wrong. And in the relativistic case, you will see that instead of a parabola, this would be a parabola. And in the relativistic case, instead of a parabola, you will have a hyperbola, right? You will have a hyperbola, which, okay, sorry. You will have a hyperbola, but it would match for lower velocities like this. It would match, and then it would go something like that. Okay, and where does it approach? Where does it approach? Okay, it approaches this line of 45 degrees. Sorry, this is parabola, and the hyperbola will be something like this. Okay, it approaches the line of 45 degree. Okay, if you have a 45 degree line here, for example, 45 degree. Okay, so parallel to it, you'll have a 45 degree line here. Okay, I think I should write. Okay, so this is 45 degree. 45 degree means speed of light. Okay, so this particle, which is under constant force, it cannot exceed the speed of light. All right, so speed will approach the speed of light like that. All right, so that's the hyperbola. This is an asymptote. This we call it as an asymptote. Okay, so the speed cannot exceed the speed of light. The speed cannot exceed the speed of light. It slowly increases as it approaches c. Then it cannot increase anymore. Okay, this is what will happen. So it's a hyperbola in the case of the relativistic particle. Right, for a Newtonian particle, it's a parabola. Okay, so I think that's. Is there any doubt? Any question?
Yes, sir.
All right. So I think we have almost completed all the topics except Doppler effect. All right. Tomorrow we'll give a general formula for Doppler effect. There is a problem with that. All right. But we'll believe that the question will be asked in a particular way. So we'll give the formula for Doppler effect, do a few problems, and then we'll wind up relativity. Okay. Relativity questions. I think it will be useful in the long run. Okay.
Sure, sir.